Hi and welcome to my channel. I'm Angela Yang and today I'll be teaching you about the ideal gas law. The ideal gas law is an important topic in chemistry because it covers the relationship that is demonstrated between different properties of a gas. So in this video, I'll be teaching you how to understand and apply the ideal gas law in a more difficult multi-step problem. I hope you enjoy.
So today we're going to be putting the ideal gas law into use. Before you start doing this problem, take a moment to review the ideal gas law and familiarize yourself with the units that are used and just the general equation itself. So I'm just going to write it down over here. PV equals nRT, where P is pressure, V is volume, N is number of moles, R is 0.0821, the universal gas constant is T, and T is temperature measured in Kelvin. So let's just jump right into this problem because it is actually a really difficult and multi-step problem. So we're going to need all the time we can have. So a 15.0 liter flask contains 2.5 atm of ethane gas and 7.0 atm of oxygen gas at 28 degrees Celsius. The contents of the flask react until the limiting reactant is consumed. What is the total pressure in the flask after the temperature returns to 28 degrees Celsius? And then we're given an equation. So we need to come up with a game plan for a problem like this. We're looking for the total pressure in the flask after the temperature returns to 28 degrees Celsius. So we know we need to find how much gas is left over when everything has been reacted. So we're looking for the number of moles of products, I assume, and also the excess reactant. So let's begin by changing Celsius into Kelvin, because that's always important, right? 28 plus 273 would be 301 K. So 301 Kelvin, and that's the same down here. So now we see that we have three units here, liters, ATM, and Kelvin. So we have three of our variables. So we're just looking for the fourth, which is the number of moles. So let's use Pivnert to find the number of moles of each reactant first. We have two reactants, C2H6, which is ethane, and O2, which is oxygen gas. So using Pivnert, we have 2.5, which is the ATM of ethane gas, times 15.0, which is the volume in liters, PV equals nRT. So N is what we're looking for, the number of moles, times 0.0821, the universal gas constant, times 301, which is our temperature. Now let's set up the same equation down here. The only difference is if you see 7.0 atm instead of 2.5. So we got the same thing, equals N times 0.0821. So that's just using Pivnert to find the number of moles of reactants. So I went ahead and did the math and found that the number of moles of ethane is 1.517 moles. 1.517 moles of C2H6, and the number of moles for O2 is 4.249. 4.249 moles of O2. So now that we have that, we can go ahead and find out the theoretical yield of each product based on each reactant. So let's start with ethane. We have 1.517 moles of C2H6. So we have that, we're going to have to do that twice, because we have two products. And right now we're looking for the limiting reactant then. So we're going to do some dimensional analysis and also using mole-to-mole ratios. So the first product is CO2, carbon dioxide. And the moles for that is 4 moles of CO2 over 2 moles of C2H6. Another thing I forgot to mention is that make sure that the equation is balanced beforehand. I went ahead and made sure that the equation is balanced, but in a lot of problems like these, the equation is unbalanced, and using the mole-to-mole ratios that you see in the unbalanced equation will definitely mess up your calculations. So our second product is 6 moles of H2O, so it's water is our second product, over 2 moles of C2H6. So you see we're using the mole-to-mole ratio given in this balanced equation to find the amount of moles produced for each product. So that would be 3.034 moles of CO2 and 4.551 moles of H2O. So that's the amount of product produced by ethane. Now let's do O2. So we said we had 4.249 moles of O2. And once again, we're going to have to do that twice. So our first product again is CO2, carbon dioxide. So that we have 4 moles of carbon dioxide, and this time we have 7 moles of O2. That's our mole to mole ratio. And the second one is water, H2O. Oops, not O2. 6 moles of H2O over 7 moles of O2. So once you multiply that out, you get 2.428 moles of CO2 and 3.642 moles of water, of H2O. So looking at this, we see that O2 is our limiting reactant because it produces less product. It produces less in each instance. So using this, we must figure out how much excess reactant, in this case our excess reactant is ethane. We must figure out how much of that excess reactant is left. So to do that, all we got to do is use the mole to mole ratio again. So 4.249 moles of O2. We said all of this reactant is going to be consumed because it's limiting reactant. So we just got to figure out, based on this, how much of the excess reactant, which would be ethane, how much of that will be consumed. So 2 moles of ethane, which is given to us up here, and then 7 moles of O2. That is our mole to mole ratio, and we figure out that 1.214 moles of ethane will be used. Now be careful here, because that tells how much ethane is actually used when all of the O2 is used up, which that is what it says when all the limiting reactant is consumed. So we must subtract. 1.517 is the initial amount of C2H6 that we are given right here, minus 1.214. Now this will give us the leftover reactant, the excess, which is 0.303 ethane, moles of ethane. So this right here, this is very important. So now back to the question, is asking us, what is the total pressure in the flask after the temperature returns to 28 degrees or 301 Kelvin? So we are just going to use Pivner again. However, we need to figure out the total number of moles of gas in the flask when the reaction is done. So all we have to do is add up the products, the moles of products, and that's all we're doing right here. And we have 6.373 moles. So you see I took the number 0.303 plus the product plus the other product and got 6.373 moles of leftover gas. So by leftover gas, I mean what is left in the flask when the reaction is done. So using this, now we can use Pivner. So we are looking for the pressure. What is the total pressure? So for P, our volume is still the same, 15.0 equals number of moles, and that is just the number that we just figured out, 6.373 times the universal gas constant times 301. So if you do that math, you get the pressure equals 10.5, and I believe I rounded on 10.5 ATM. So the total pressure in the flask after the temperature returns to 301, which is 301 Kelvin, you get 10.5 ATM. And that right there is our answer. Awesome. Well, thank you so much for watching this video, and I hope it helped you with your understanding of the ideal gas law and being able to apply this understanding in a multi-step problem. Leave any questions or requests in the comments below, and I hope to see you back here soon.